Interesting. Okay. So apparently we're live. I'm going to sit here for a little bit and prepare my screens. Think about how to do this. So I don't know if you've been paying attention, but recently some scientists did an analysis of protons and decided that protons were quote-unquote maximally entangled, which basically means like, there's like pretty much as you can get into a proton. That they were basically like black holes is what they started to say, but then they wanted to back off of that because there seems to be some just like strange obsession with not like avoiding this black hole thing, which solves everything. I mean, it explains so much. Okay, just accept black holes as being a trick of the geometry of the universe. Don't avoid them. Don't pretend like they don't exist when they sort of really seem to. Like, for instance, the observable universe thing. You know? Okay. Really? There's actually somebody watching? That's absurd. Announce yourselves, please. Anybody that's actually there, that's absurd. I don't believe it. I think it's a trick of the website to like automatically insert somebody. Dude. Okay. So let's get something straightforward. This is going to be all about nuclear decay cosmology because that's all I can think about. Neutron decay cosmology, as I like to call it. And for the simple reason that neutron decay, neutrons, and then neutron decay, if you watch my previous video, is basically what I consider to be the fundamental process of the universe, the motion from a neutron to a decayed neutron, which is a proton, with accompanying electron field and a antineutrino. And I will say an antineutrino because the charge came off. So it's antineutrinos. Neutrinos put charge onto things. Antineutrinos push charges off of things, uncouple the charge. Okay. This is tiny. This is 1 neutron, the size of 1 neutron. Tiny. And this is 1 meter. So we expanded from 1 Planck practically. Planck would be at par. I don't see what you mean. Planck would be at par. Planck size varies in my model. It's a very important thing. It's like fully Lorentzian in that way. Okay, but this is it. Okay, neutron hits event horizon. Neutron becomes vacuum energy. Neutron re-emerges in lowest energy density places. Highest energy density? I don't know how you do maximum. Boop. And energy? Minimum. This is simplicity. Then you fall, basically, like that. Your entire existence is a very gassy proton and electron, a very, very, very nebulous hydrogen that slowly over time gets compacted and turned into a planet, maybe some water, and then that gets absorbed by a sun until you are neutronium. And then the next step past neutronium is where two neutrons actually touch. And now this membrane of light becomes one continuous membrane of light, which is the universe. This is the vacuum energy, which is this. And then to compensate, when a neutron crosses, one neutron is ejected. And now fine-tuning is achieved continuously. In terms of the manifold, though, it's very important to realize that time is an infinitesimal. It is the infinitesimal. It is a Planck. It is the thickness of time. The entirety of time is a Planck rotation. And is that Planck rotation, this is a whole rotation, because this is two-dimensionalized 3 dimensions. So compacted, sort of like reduced. So that's a half rotation from the past into the present into the future. Okay, there's a whole rotation of something. Now electron, there's a whole rotation of electron, but co-joined with that is a whole rotation as a positron on the other side of the universe. Which is why electron half spin. One orbit electron, one orbit positron, one orbit electron, one orbit positron. I mean, it's happening continuously, but the orbit length is 2 orbits long because it has to do an orbit on each side. Everything needs to be on both sides. Let's start with space, though. Okay, space is just space. You measure the density of space according to the energy density in that location. And I have nobody watching anymore. Why am I doing this? I don't know. Is there anybody? There's still somebody. You're watching. Hello? Like, anyways. You have a meter of space. Cubic meter of space. This is a value of 1. You can get 1 neutron. That's the lowest amount you're allowed to have, is 1 neutron, apparently, in this world. 1 neutron is the minimum. Okay? And then, as you add energy, what you've done is compress space. Think of it thermodynamically. You just have the volume. You just doubled the energy density. Have the volume. Double the energy density. Half 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 the volume. Double the energy density. Oops. Don't you want this? Half the volume. Double the energy density. Half the volume. Double the energy density. Half the volume. Double the energy density. Okay. This is the way we need to think of it. Distance and energy, and it's all the same. it's all the same. It's like a fully Lorentzian thing in that if you have twice the energy in a space, then really what you have is twice the space compressed into the same space. And that's how you can account for it. So that here's a black hole, or even just a planet. Yeah, let's just say here's a meager kind of planet. And these are like unitational gravity things, gravity lines. And as you're a photon and you cross that line, and you know that it's going to veer you 1 degree, right? And then you go. That's how much you're going to get veered by that gravitational field, right? Because the Plancks are this big, but now we're going to have the Plancks. Plancks are going to be half as big, twice as dense, energy dense. Now this photon gets veered a degree, it gets veered a degree, it's veered a degree, maybe even way over here gets veered a degree. Okay, so now it gets veered more. Then let's put some more energy into that space. And now it gets veered more. And there is the point at which the energy density is so high that basically all that happens is you get complete internal reflection. You're not moving forward, you're moving sideways with every step, which means you're now trapped. This is exactly what we are. Okay? Regular energy dense space a little bit. Once you dense space, so you're going 90 degrees, now you're trapped over your own orbit. This is a piece of matter. It is one photon trapped over it. This is a lump of light. It's a tiny little piece of light. Tiny little sphere of light. And this sphere of light exists in a whole, sort of embedded on a whole sheet of light, which is the vacuum energy. Okay, here's a neutron or a proton. This is a mass unit. One photon trapped over its own energy. You can also think of it as a unipolar dynamo. I mean, not a unipolar, like an electrostatic motor, super simple electrostatic motor, though people get mad at me when I say things like that. In that, the permittivity and the permeability of space means that this positive charge, once this gets rotated, this positive charge is diminishing, but this negative charge is attracted to this positive charge. And the balance of these two effects, the attraction of this negative to the positive charge and how fast this charge dissipates, because at the same time this is being a negative trail that this positive being is being attracted to, determines the speed. This is how C, in a way, comes out of epsilon alpha and epsilon naught and mu naught. Okay, because that's what it has to do with. How fast the magnetic field, electric field dissipate. And therefore, the dissipation rate determines how fast things could move and determines Planck size. Which means that higher energy situations will have a different value. So there we go. And then, so much expanded. Here's a regular mass unit with a proton. There's an added positive charge, which I say is an outflow. It's an outflow from the past into the future, because the future is more dense. Gravity says so. Okay, there's one direction, there's inward. The future works that way. Okay, so this is the usual composite, where there's the nucleus, the nucleons. When there's only one, it's very simple. When there's a cluster, then you get a complex electron cloud, because these are inversions of each other. This and this are mirrors of each other. This is the expressed, the electron cloud is the expressed form in here we really need to look at. what is the shape of the electron clouds on the more complex metals, etc., like larger ones, and then just invert them. Do the math trick of inverting them. Create a complex electron orbital, then flip it inside out. And that should, in theory, tell you how the orbits of the neutrons and protons or whatever work out, how that balances, how those fit together. They don't necessarily have to be spherical anymore, because now it's a resonance inside of a chamber. Okay, this is like some complex waveform, but that waveform, when everted into an electron cloud, they should be mirrors to each other. This is the laws of reciprocity, the law of conservation. I say law, it's not a theory of conservation, it's a law of conservation. And people say, no, it's not. It's like, yes, it is it. And you say, the only reason you could say it's not is because gravity is giving energy to things. But we get that energy back. This is the whole point of neutron decay cosmology. What happens if everything is imbued with energy constantly? And when we imbue things with energy, they get more dense and less viscous. And then all of a sudden, it's the same thickness, same size as the membrane itself. And so it becomes the membrane. There's gravity. There's gravity. You're falling down a hill. That's all. You're falling down the hill of this having gotten smaller and denser and more viscous. I mean, less viscous. And up here, and let's say you're spinning at a certain rate. Here you're spinning. Here it takes 4 rotations. Here it takes 8, 16, 32, 64, 128. It takes 128 rotations here to make this go around once. So the relative speed of this is very low. Therefore, it's like the angular momentum, all of the energy associated with this is very low. It's a larger thing. It's more viscous. Less viscous. That's what draws us in. Then all of a sudden, at event horizon, you become the vacuum energy. You get ejected out to where one of these super, super giant, but very low energy things just created a gap, and you insert yourself into that gap. Then you expand using neutron decay. You correct the entire thermodynamic gain from gravity. This is the gain back. It's like the big numbers thing with Dirac. You get compressed, you get ejected, you re-expand up to maximal. You get recompressed, you expand, get recompressed, you expand. Okay, this is thermodynamics. This is essential. You compress something, the temperature goes up, the energy density goes up. You compress something, the energy density goes up. You reached a limit. Your valve is about to burst. So what you do is you let it out into the room or into the lowest pressure place you can find. Okay. It's very simple. And what happens is, here's an energy. I think I drew this graph the other day, but just to reiterate, because I'm annoying that way. Okay. Here, this direction is going to be energy. This along here is going to be refractive index. Okay, because we're making space a thicker substance by making it more dense with energy. Therefore, it's going to cause more refraction. You see, there's no refraction. It's like, whoa, what happened there? This is the way some of these logarithmic things work, you know? Seems like nothing, and then boop. At a certain point, your refractive index is such that you have full internal refraction. Okay, this beam came in here, bounced out here, is being reflected inside this forever. Think about it though. This passage of this energy in this general direction and bouncing off that pulls the surface inward, maintaining the droplet itself. This is probably where Navier-Stokes comes in and all of this. That, like, you know, this tension on a droplet is sort of like the tension of the internal reflection of the energy, because this is all pulling in, and because it's pulling in, this energy is higher density than this side. Therefore, it pulls inwards. It's actually like pulling inwards as much as it can equally, and therefore you get the sphere. And it's simply the fact that when you're on the wrong side of a curve or on the right side of a curve, this is dissipative. And this is concentrating. It's all geometry. It's all geometry in the end. And this is what it's like. This matter, a little ball of light. The universe itself, this layer of light, folded in on itself by gravity. I'm going to try and do the rest of Neutron Decay Cosmology, going through the notebook in the next few days.